Okay, this problem involves a spring being compressed, so that means we're going to have to use work energy to figure everything out. So let's draw a diagram. Let's see what's going on here. So we're on a 37-degree incline, and we have a 5-kilogram mass. Sliding 1.2 meters down an incline. Where it compresses a spring that is oriented parallel to the incline. And it compresses the spring an additional 0.25 meters in addition to the 1.2 meters. So the total distance it travels down the incline is 1.45 meters. The spring constant K is 1200 newtons per meter. And we want to know what is the work done by kinetic friction during this motion. Alright, so well, let's identify the forces that are acting on the mass. So we've got mg, normal force, kinetic friction, and then the spring force is also going to push the mass back up the ramp. It's not acting up here where the mass is, where I've drawn it, but it does act on the mass eventually. Alright, so I've got all the forces, right? There's no tension and there's no applied force. So that's it for the forces. I've got the displacement. I guess I need to establish a sign convention, so we'll make down the ramp positive and out of the ramp positive for our sign convention. Okay, so let's see. So the next step is to calculate the works done by each of the forces. The work done by the normal force is 0, of course. It's perpendicular to the motion. The work done by gravity is positive mgh. Right? It's minus change of potential energy. So the change of potential energy mgh is positive because it points down. Now the height in this one, if I draw a triangle that represents the delta S of 1.45, and that's 37 degrees, and here's the height. So height is equal to 1.47 or 1.45 sine 37. So this is 5 times 9.8 times 1.45 sine 37. So the work done by gravity is 42.76 joules. Okay. The work done by the spring force takes on the form 1/2 kx squared. And in this case it's negative because the spring force opposes the motion, so that's minus 37.5 joules. Okay, the work done by kinetic friction is unknown, and delta K, final kinetic energy minus the initial kinetic energy. Well, we are told that the spring reaches a maximum compression, so that's 0. Right? The mass stops once the spring has its maximum compression, just like a max height problem. And then we're also told that it starts at rest. So delta K in this problem is 0. Now, we have to find the work done by kinetic friction. I kind of left a question mark there, but right, so remember there are 3 different ways to find the work done by a force. You know, we could try mu sub k times the normal force times delta S times cosine 180. But we don't know mu sub k. So, and that's not really what we're solving for, right? I mean, we don't know the work done by kinetic friction, so you know, I guess I could solve for mu sub k and work it out that way, but I think it's easier to solve it where we say, well, the work done by the normal force plus all the other works in the problem is equal to delta K, because I know the work done by the normal force, I know the work done by gravity, I know the work done by the spring force, and I know the change in kinetic energy. That enables me to solve for my unknown. I think that's easier. So, if I solve for the work done by kinetic friction, I get minus 5.3 joules. Now, if I needed to go back and find the coefficient of kinetic friction, I could certainly do that, but that's all I need to do for this problem.